Let's continue with the rules for sketching the root locus. To find the points at which the root locus intersect the imaginary axis, we resort to the root criterion. Remember that when a whole row in the root array is 0, the roots of the auxiliary equation are also roots of the characteristic equation. So what we do now is to find the values of v, of the varying parameter v, for which a whole row is 0, and then we use the resulting auxiliary equation to find the crossings. So let me illustrate that with an example. In this example, f of s has two poles at -1 plus j and at -1 minus j, and a 0 at s equal to 1. So to find the crossings with the imaginary axis, we rewrite the auxiliary equation like this: s squared plus 2 plus vs plus 2 minus v equal to 0. It is easy to get from this to this arrangement, and from that we can write the root array in which the parameters are 1, 2 plus v, 2 minus v, and 0. And now it is very simple to finish it, because this has to be 2 minus v. So as you see, for v equal to -2, this whole row is 0, and the corresponding auxiliary equation is s squared plus 2 minus v, that's 2 minus -2, or 2 plus 4, equal to 0, or in other words, s is equal to 2 minus to plus minus 2j. So the intersection takes place at 2j and minus 2j. Also, notice that this is a negative value of v, whereas here the value of k is 1. So the signs are different, and this crossing has to be part of the negative root locus. So if we draw the whole thing, this is the negative root locus with its part in the, or its branch in the real axis. And if we draw the rest of the root locus, this is actually a circle, and the blue part is the positive root locus, which also crosses the imaginary axis, but it does it in the origin, just as this part of the array is telling us, because at v equal to 2 we have this whole row equal to 0. So the root array is also telling us where the positive root locus is crossing the axis. Okay, the next rule defines breakaway and breaking points. They appear in the real axis when there's a piece of root locus or branches of the root locus between two poles, and since in those two poles two branches begin, they must try to somehow find a 0 to end. So they must leave the real axis in order to find those zeros, and the point in which they leave the real axis are called breakaway points. Similarly, if we have two zeros with root with couple of branches between them, they must come from somewhere. They must come from some pole, and the point in which the branches arrive to to the real axis are called breaking points. Well, we can find both breakaway and breaking points because V has to be either a local minimum or a local maximum at those points. In particular, breakaway points appear at maxima and breaking points appear at minima. So to find them, we can always rewrite v times f of s equal to -1 in the following way. We can isolate v, which is equal to -1 over f of s, and in doing so we're writing v as a function of s, a function we can differentiate dv over ds in order to find its local maxima and minima. Again, let's illustrate this with an example. In this example, f of s has poles at 0 and -1, so there's positive root locus between them, and zeros at -2 and -3, and there's also positive root locus between them, so there must be a breakaway point in this branch and a breaking point in these two branches, in this area and in this area. And we can find them by rearranging this as v equal to minus s squared minus s over s squared plus 2 plus 3 5s plus 6. So now we can differentiate dv over ds is equal to 0, and that, if you work out the operations, lead to minus 4s squared minus 12s minus 6 equal to 0, whose solutions are s equal to minus 2.37, which is a minimum, or in other words, it is defining a break in, just as we expected, because it is here. And this takes place for v equal to 13 plus 93. And the other solution is s equal to minus 0.63, which is a local maximum, and therefore it is defining a break away, just as we expected, because it's between two poles. And this takes place for v equal to 0.07. We could have seen that these are actually minimum and maximum if we had drawn this function, this v of s here. We would have found something like this, with its minimum here and something like this. Well, let me try again. Something like this, with its maximum here. But anyway, this is not root locus. You must be careful with that. The root locus is something like this. I was just drawing that to point out the fact that they come from maxima and minima. So this is the positive root locus. The negative root locus in this case is very simple. These parts of the real axis belong to the negative root locus. Although this is a pretty interesting example, because we have one branch of the negative root locus between this pole and this 0, and also it seems like we have two other branches, but actually that is not the case. They are the same branch. The only thing is that in this part v belongs to minus infinity minus 1, and in this part v belongs to minus 1 0, but they're actually the same branch. It sort of starts here and ends here. You can also run into other weird cases, like, for example, a 0 and a pole and root locus between them. This goes like this, but if you draw v as a function of s, you may find that between these two values you find both a minimum and a maximum, so there are both break-in and breakaway points. So here the root locus is arriving to the real axis, and here the root locus is, or branches of the root locus are leaving the real axis. And an even more strange case takes place when instead of a minimum and a maximum, we find a saddle point, which is neither a maximum nor a minimum. And in that case, what we find is that several branches arrive and leave the root locus at the same point. So we have this branch going in this direction, and also these two branches coming in, and these two branches leaving the root locus. Another interesting case is the one in which there are break-in or breakaway points in complex positions, not in the real axis, but in complex positions. And you can find them by doing the same thing, dv over ds equal to 0. Although in this case this is only a necessary condition. Sometimes we run into solutions for this equation, complex conjugate solutions, for which s does not belong to the root locus. If you want to practice that, you can use the following example: s times 1 over s times s squared plus 2s plus 2 equal to minus 1. In that case, the solutions of dv over ds do not belong to the root locus. So the criterion is sort of misleading us, because it is telling us that there are breakaway or break-in points in some position in the plane, and that is not the case. But that never happens when dv over ds equal to 0 has solutions in the real axis. When those solutions are in the real axis, they're always either a break-in point or a breakaway point, which may belong to the positive or the negative root locus. Let's go with the final rule. Angle of departure from pole or arrival to 0. When f of s has poles or zeros which are complex conjugates, the root locus must arrive to them or leave them, and it does so according to certain angle, and the angle can be calculated using the following formulas. Here are the formulas. They're just the angle condition applied at a point infinitesimally close to the pole or the zero we are analyzing. So this is the angle from the other zeros to the pole. This is the angle from the other poles to the pole, and this is the angle of departure from the pole. This has to be equal to 180 degrees. And in the case of the negative root locus, this has to be equal to 0 degrees. which means that the angle of the negative root locus is simply the opposite angle of the positive root locus. And the same for the angle of arrival to 0. This is the angle from the other zeros to that 0. This is the angle from the other poles to that 0, and this is the angle of arrival. So let's do an example and finish the video. In this example, there are 3 poles and 1 0. This is at -1, this is at -2 plus j, -2 minus j, and -3. So what is the angle of arrival to this 0? Very easy. This angle is 45, so 45 degrees, minus this angle here, which is 90 degrees, minus this angle here, which is 135 degrees, minus the angle of departure from the pole, is equal to 180 degrees, which means that this is equal to 0. So the root locus leaves this pole like this, and it does the same for this pole because of the symmetry. Therefore, the negative root locus leaves the pole in the opposite direction, and you can complete the root locus. It's something like this. For the negative root locus, we have this, and for the positive root locus, we have this part and a couple of asymptotes that of course you could or you would be able to calculate now. Okay, I think we're done. The only thing that I like to do now is to encourage you to solve as many root loci as possible, so that you become experts in drawing root loci.